So over the last few classes, we've been talking about reversible and irreversible processes. We know that reversible processes are ideal, but that they don't really exist. But even though they don't exist, it's helpful to understand what the ideal process looks like because it gives us the limit of our performance. And it can give us some equations that help us to see how we can get better performance out of a real process. So knowing the ideal process can help us define how we're doing. Today, we're going to focus on what we call isentropic efficiency. So before we look at isentropic efficiency, let's just recall the second law and how we apply it to turbines and pumps. So for ideal turbines and pumps and real turbines and pumps, we have approximations or assumptions that look a little bit different, right? So both of these types of components, real and ideal, will be steady state. They'll both be adiabatic. So the real process is going to look something like this. Sigma dot is equal to the sum of m dot out s out minus the sum of m dot in s in. But in a reversible or an ideal turbine or pump, there are no irreversibilities. What that means is there's no way in this ideal process for us to generate entropy. So that sigma dot term goes to zero. And if the pump or the turbine is one inlet and one outlet, and it's at steady state, then the mass flow rate into the turbine or pump is equal to the mass flow rate out of the turbine and pump. So then this equation would tell us that S at the outlet minus S at the inlet of a reversible process, if it's steady state, one inlet, one outlet, and adiabatic, would be zero. But if the process was irreversible or real, there are reversibilities, so sigma dot would be positive because in any real process we're generating entropy. And that means that even if it is one inlet, one outlet, steady state, adiabatic, we're going to get that the outlet entropy of my turbine or my pump is bigger than the inlet entropy. So S2 minus S1 would be greater than 0 kilojoules per kilogram. Remember, this is why we started to draw these kind of processes on TS diagrams instead of TV diagrams. We like these because we can see really easily whether or not a process that goes through a turbine or a pump is ideal, real, or impossible. So here we're going to move from S or from state 1 to state 2S. Remember, we add the S to state 2 here to denote that this is the isentropic outlet of the turbine. In this case, the ideal outlet. The real outlet, we know that S2 has to be bigger than S1. So the process through the real turbine goes down and to the right on our TS diagram. If we're talking about a pump, we know that the isentropic outlet of our pump, here 4S, is vertically above state 3. And because the real pump increases its specific entropy as the fluid moves through it, S4 is up and to the right on our TS diagram. So how do we deal with an ideal turbine? We get enough information to fix a state, right? Remember, this is always going to be the tricky part. And when we're doing these cycles, we're going to make these state tables. And in the state table, you'll see that you'll usually have one or maybe two states where you know two independent intensive properties. But then oftentimes you won't have that information in the next state. So we can use the idea of an ideal turbine to help us fix state 2S, and then we'll see how to fix state 2. So we might know enough information to fix the inlet of the temperature of the turbine. Maybe we know the temperature and the pressure here, but maybe we're only told the pressure or the temperature here at state 2. So then we can find state 2S because we get that second independent intensive property, because we know that S2S is equal to S1. And that gives us that extra piece of information that we can use to fix at least this isentropic outlet of the turbine. We'll usually have some other property here in addition to the extra specific entropy here that we get because we know it's the same as state 1. We'll get some other piece of information on our state table, like maybe we'll know the temperature or the pressure of the exit at the turbine. Then we fix the state using a table, right? In this case, here, if my diagram is correct, state 2s would be under the vapor dome, so I try to find the quality at state 2. But if I just, because this is just a sketch, so maybe this would really be out over here, and I'd be a superheated vapor coming out of my turbine. It's a similar thing for pumps, but remember, pumps are a little bit different, right? We talked about how do we find delta H across an ideal pump. We've talked about this before, and we know that delta H is equal to approximately the specific volume times the change in pressure. But that's when we have an ideal pump. And remember when we introduced this equation, we talked about this ideal pump as having the same inlet and outlet temperatures. So if we have a pump with the same inlet and outlet temperatures, we can see from the equation we introduced last class that delta S, if the inlet and outlets are subcooled liquids, is equal to Cp times the natural log of T2 over T1. But if T2 is equal to T1, then this natural log goes to 0 and delta S is 0. So this ideal pump, which before we had described as having the same inlet and outlet temperatures, would actually have 0 change in the specific entropy of the fluid. So it would be an isentropic pump, which in this case is an ideal pump because we've also made the assumptions that the process is at steady state, adiabatic, and has one inlet and one outlet. So today's lecture is going to be about how do we find the real outlet state from our turbine and from our pump. And the way we're going to do that is we're going to define a new variable called isentropic efficiency. So how do I find the real outlet from the turbine and the real outlet from the pump? I know that the ideal outlet or the isentropic outlet is vertically down from the inlet to the turbine or vertically up from the inlet to the pump. And I also know that the real outlet from the turbine is to the right of the ideal outlet, and the real outlet of the pump is also to the right of the ideal outlet. Here, in this case, I'm assuming that what I know at the exit of the pump is the pressure and not the temperature. Just like at the turbine here, although these are both look like they're at the same temperature, I'm going to assume that I'm measuring my pressure as I come out of my turbine. So we have this new term, and we call it isentropic efficiency. So we know that the word isentropic means that the entropy of the system does not increase, or at least that the entropy of the fluid moving through the system does not increase. So here, both in the isentropic turbine and the isentropic pump, delta S, the change in the specific entropy, is 0. It's kind of another word for ideal, although I guess technically to get from delta S is equal to 0 to sigma dot is equal to 0, in the second law, we have to be assuming things like the process is at steady state, the process is adiabatic, the process is one inlet and one outlet. So it only really makes sense for us to talk about isentropic processes when we're talking about things that are adiabatic, right? So things like turbines and pumps. You wouldn't really talk about an isentropic heat transfer process. So it is ideal if we're assuming that the process is steady state, one inlet, one outlet, and adiabatic. So isentropic efficiency. So anytime we use efficiency, we'll use the Greek letter eta. So it looks like a fancy scripted N, right? And here we can define the isentropic efficiency for turbines and the isentropic efficiencies for pumps. And we're going to see that thematically or maybe fundamentally, these are kind of the same concept, but the equation for the turbine is different than the equation for the pump. But what this does, the isentropic efficiency, it compares the performance of my actual turbine or my actual pump to the best performance a turbine or pump could ever have, right? To this ideal performance. So because we're comparing something real to something imaginary, right? Something ideal, we know that ideal performance is the best we could ever have. So we must be getting less than 100% efficiency when our efficiency is isentropic efficiency, because our turbine is going to perform worse than the ideal version of that same turbine. So we define these isentropic efficiencies by comparing the ideal process and the real process. But the way that we do that is we talk about the energy benefit of the different process. And for both turbines and pumps, the reason we're running these processes, right? So we run a turbine to extract power from high enthalpy fluid. And we run a pump to add power so that we can increase the enthalpy in the fluid. So for turbines, we go back to our first law, and we're trying to find now an equation for the power developed by this turbine. We know that we have a steady state turbine, that we're going to neglect changes in elevation, changes in kinetic energy. We're going to say that it's well insulated, close enough to adiabatic that the heat transfer rate is much less than the power that's generated. And typically we'll also say that it's one inlet and one outlet. And if we do that, we'll get this equation, which hopefully is becoming familiar by now, that the work or power term generated by this turbine is m dot times h in minus h out. So if we were talking about the ideal turbine, then this ideal turbine, this equation works for the ideal turbine. The inlet is the normal inlet that you would see in both the real and the ideal turbine. But the outlet for the ideal turbine is H2S, the enthalpy that I would find if the specific entropy was constant. For the real turbine, I'm going to have the power be the mass flow rate times H1 minus H2, where H2 is the actual outlet. So now, I want to have my isentropic efficiency be the ratio of these two things. But I also want my isentropic efficiency to be less than 100% or less than 1. So I got to ask myself, which of these two terms is bigger? So which of these two terms should be in my denominator? So the turbine's purpose is to produce power. So I have this ideal turbine and it's producing some amount of power. Now what happens is there's friction in the turbine. So let's say we just got this shaft and it's spinning, and there's bearings in that shaft and there's some friction in those bearings, right? So that extra friction means that some of the power that otherwise I would be able to harvest in the ideal case is going to overcome that friction. So what happens is the real turbine doesn't produce as much power as the ideal turbine. So here, the bigger number is the power produced by the ideal turbine. So now I want to define isentropic efficiency of my turbine. Isentropic efficiencies are always going to be the power divided by the power. And one of these terms is going to be the ideal term, and one of them is going to be the real term. And I have to put the bigger number on the bottom. So as we just discussed, the power generated by the ideal turbine is bigger. So the ideal power is bigger than the real power. So that means in this case, our isentropic efficiency is going to be the power generated by the real turbine divided by the power generated by the ideal turbine, because we need this isentropic efficiency to be less than 100%. So the way that I try to think about this is that the purpose of the turbine is to produce power. But remember, the universe always takes a cut from every one of these energy transactions. So what happens is that the irreversibilities in the system make it so that we can't produce as much power as we would in the ideal case. So the real turbine always produces less power than the ideal turbine. But what about the pump? We can do a similar analysis for the pump, And remember, when we do the first law analysis for pumps and turbines, it ends up being basically the same thing. So my assumptions, I'm going to assume that the system is at steady state, that there's negligible change in elevation, negligible changes in kinetic energy, that the system is well insulated or adiabatic, and that there's one inlet and one outlet. And again, hopefully this is not surprising. We get that the power consumed by the pump is m dot times h in minus h out. For my ideal turbine, or my ideal pump, now we're moving between state 1 and state 2 in this case. So my ideal pump is going to be m dot times h, the inlet of the pump, minus the outlet of the pump. But the ideal pump has the isentropic outlet, right? And remember, because this is a pump, we know that work in is negative. Here we're putting work into the system. So we would expect H2S to be bigger than H1 in this case. I can use this same equation for the real turbine and get that m dot times H1 minus H2 is equal to the power consumed by the pump. So now we get to this question again. Which one of these two terms is bigger? So in this case, when we're putting power into the system, we not only have to add enough power to increase the enthalpy, we also have to overcome all that friction. So here we need to put more power in the real case than we do in the ideal case. So this is what makes pumps and turbines a little bit different, and it's partly because the signs of these two things are different. So here, the ideal pump would be able to increase the pressure of the fluid with consuming less energy, right? So less current draw into the pump. But the real pump, because it has to overcome things like friction, it needs to consume a little bit more power to get that same change in the pressure. So the isentropic efficiency for the pump looks like the isentropic efficiency for the turbine, where it's going to be power over power, and I have to remember which one is ideal and which one is real. Now the tricky part here is that it's different for turbines and pumps. So in this case, the real power consumed by the pump is bigger than the power consumed by the ideal pump, right? It's always like the universe is working against us, right? So we want to produce power with the turbine, so we produce less than we would in the ideal case. We would actually like not to consume power for a pump, so we end up consuming more power than we would in the ideal case. So here we get that the isentropic efficiency for the pump is the power consumed by the ideal pump divided by the power consumed by the real pump. And again, if you ever do this and you get an isentropic efficiency bigger than 100%, it means that you got the ratio upside down. So now we come to the question of how do we fix the states? Now this is obviously important in thermodynamics. There's kind of two parts to every problem. The first is demonstrating that you understand how to get a symbolic solution from first principles. And then the second is going to be how do you get a numerical solution by fixing the states. So when we have these ideal turbines or isentropic turbines and pumps, we can fix the state by using the fact that S2S is going to be equal to S1, or S4S is equal to S3. This is, like we said, this is sort of where the outlet state would be if the process was isentropic, which means ideal under the set of assumptions we've been talking about. But in reality, we also know that state 2 is to the right of state 2s, and state 4 is to the right of state 4s. But how do I find state 2 and state 4? Right, so now we've talked about this idea of isentropic efficiency, and we know that that what happens is the irreversibilities in these processes make it so that we don't get as much power as we would from an ideal turbine, or we have to put more power into an ideal pump. But how does that information help me? And we'll see, there's kind of two ways to sort of think about this. So sometimes we get enough information to fix the states, and the problem will ask us, what's the isentropic efficiency? And sometimes we won't get enough information to fix the states, and we'll have to use the isentropic efficiency to find the real outlet state. So here's an example for a turbine where what we're trying to do is find the isentropic efficiency. On my state table, I have state 1, where I have a temperature and pressure. I'm expecting this to be a superheated vapor. State 2, I only have the temperature, but that's okay because this is state 2s, right? So state 2s is always going to have the same piece of information we have about state 2. It's just we'll usually only have one piece of information. So it'll usually have either the same pressure as the real outlet or the same temperature as the ideal outlet, because we want to compare what the ideal turbine power would be if it was operating between the same properties, right? Or the same, they're not exactly the same states, but if we're reducing it down to a particular temperature, we want to know, okay, what's the ideal power we would get if we reduce that enthalpy down, or that fluid, the steam, down to the same temperature. So here we want to find the isentropic efficiency of the turbine. So how do I fix the non-ideal state? Right? So first I want to fix the ideal state. So in this case, I'm given enough information to fix state 1, right? That's the inlet to the turbine. So here, I won't go through the interpolation with you, but because I know the pressure is 10 bar and the temperature is 600 degrees, I go to my superheated vapor tables and I can find the specific enthalpy and the specific entropy of that fluid. Now, how do I find the ideal outlet of the turbine? I only have the temperature here, 45 degrees, but because this is state 2s, I know that the entropy, right, this is isentropic. So I know that the entropy here at state 2s has to be the same as the entropy at state 1. So that means I can go ahead and drop this number down from my state table to the row for 2s. Now I know the specific entropy and I know the temperature. In this case, we would find that this specific entropy is between HF and HG for a temperature of 45 degrees. So I find out that this is below the vapor dome. So now I can find S2S, or I can use the fact that I know S2S to find X2S, right? So here I know S2S. I know SF because I looked it up. I don't know X of 2S, but I can find SFG because it's SG minus SF. So now I can find the quality, and the quality is pretty close to 1. So this is mostly the saturated vapor, but there's a little bit of saturated liquid in there too. But now I know the quality. And because I know the quality, then I can find H2S using the same equation for quality, but now looking at the specific enthalpies. So now H of 2S is going to be HF plus X2S times HFG. I don't know H2S. I find HF in the textbook. I now know X of 2S because I found that using the specific entropy. And I can find HFG because it's in the textbook. So now I can see that H2S is equal to 2,540, and I drop that into my table. This does make sense, right? Because I know that turbines have positive power, so H in minus H out should be positive. And I get that, right? So this is good. I feel reasonably good about this number. Now, how do I find the real outlet? In this case, we know how to do this because we have two independent intensive properties. I know the temperature and I know the quality. So I can look this up in a table. So I know that S2 is going to be equal to SG because quality is equal to 1. I don't necessarily have to find S2 here, but I like to look. And now I see that this does make sense because S is increasing, which is what I'd expect for a turbine to get positive entropy generation. And now I can find H2 by just finding Hg on this same row of my two-phase table where the temperature is 45 degrees. So I can look this up, and now this is 2,583.2. So we didn't reduce the enthalpy of the fluid quite as much as we did in the ideal turbine. So I can find now the isentropic efficiency. I remember for the turbines, because they're producing power, ideal turbines are going to produce more power. So I put the ideal property on the bottom. I know from the first law that the equation for both of these things are m dot times h in minus h out. I have the same mass flow rate in the ideal and real turbines. Even though I don't know the mass flow rate, I see that it's going to drop out. I know H1, I know H2 now, I know H1, and I know H2S. I don't know the mass flow rates, but like I said, that's okay because it's the same mass flow rate that would go through the real turbine and the ideal turbine, because we're talking about an ideal turbine that's operating under basically the same conditions as the real turbine does. So these mass flow rates just drop out. I can put some information in here, and I see that my isentropic efficiency for this turbine is 96.2%. That's pretty good. I'm getting almost as much power out of this real turbine as I would out of an ideal turbine. Now, if I was running something like a nuclear power plant, it would save me a lot of money, right? Or I'd have to burn a lot less fuel if I could increase this efficiency. But 96% seems pretty high, right? So we're pretty close. So now, if I was dealing with a pump, or I could do this with a turbine too, but there's another way to use isentropic efficiency. So sometimes we'll be asked what the isentropic efficiency is, and we'll calculate it like we did in the last example. But sometimes we'll be told what the isentropic efficiency is, and then we'll have to use that information to find the real outlet. So now, here is an isentropic pump. Again, I have enough information to fix the inlet to the pump. I know the temperature is 45 degrees and the quality is 0. So this H is going to be HF and S is going to be SF. So I just put that information in. Now, maybe you remember, right? But when we go through ideal pumps, we're going to use this equation, specific volume times the change in pressure. So what I've done here is I have added, right? So if I look at this table, this is a two-phase table. I look for the row that has 45 degrees. Hopefully it's there. Otherwise, I have to interpolate. But the next column over is going to be what's the pressure. So this is what is the pressure for water to be boiling at 45 degrees. So here we see that the pressure is pretty low. So we put that into our table. So now, how do I deal with this ideal or isentropic pump? I know that the entropy at the outlet is the same. So if that's true, if I have this isentropic pump, then I have this equation where the change in the enthalpy across the ideal pump is going to be the specific volume multiplied by the change in pressure. So really on my state table, I should have also written down the specific volume over here, but I didn't do that, right? But I did look it up in the table, and it's about 1 over 1,000, because for water, it's almost always right about 1 over 1,000, right? Here, I'm doing H4 minus H4S minus H3, but I could flip this around. If I flipped this around, then I'd have to flip the pressures around. Notice that even though in my state table, I've written pressures in bar, I prefer to write these in kilopascals. So I remember that 1 bar is 100 kilopascals. So 10 bar is 1,000 kilopascals. And the pressure at state 3 is 9.6 kilopascals. So now I can do this, right? So this is another thing, you know, if people are going to mess up this equation, it's the units, right? So you got to get the units right. Make sure that your pressures go to kilopascals here, right? So this is close to 1,000 multiplied by close to 1 over 1,000. So my answer here is close to 1 kilojoule per kilogram. So that's the difference. And remember, we're putting energy into the system as we go through the pump. So we're increasing the enthalpy of the fluid. So my enthalpy that I'm increasing here is 189.45, about 1 kilojoule per kilogram, bigger than it was in the inlet. So now the thing that I know is that my isentropic efficiency is 0.9, right? Or my pump is 90% efficient. I can use this information to find the outlet state, because here I'm only told that the pressure is 10 bar. I don't know anything else, right? So I can't really fix the other state, except that I know the isentropic efficiency. So because I know the isentropic efficiency, in this case, right, we know that the ideal pump consumes less power than the real pump because we would try to minimize the power that we're consuming here. So now when I write my equation for the efficiency of the pump, I get m dot times h in minus h out on the top and the bottom, but my ideal outlet is on the top and my real outlet is on the bottom. Again, the mass flow rates between these two states are the same, right? So it's the same through the ideal pump and through the real pump. And now I can break this down and get an expression for H4, which is the thing that I don't have here, right? So this is, we're just going through the math, right? So first we've flipped the equation here. Now we know H3, we know H4S, we know the isentropic efficiency, and we know H3, right? So here, if we're trying to find H3 minus H4, then we would get -1 kilojoule per kilogram. That's the difference on the top, divided by 0.9, and that's going to give us -1.11 kilojoules per kilogram. So whereas through the ideal pump, we increase the enthalpy of the fluid by 1, through the real pump, we're going to increase the enthalpy of the fluid by 1.11. So here, right, we've consumed a little bit more power in the real pump than in the ideal pump. And that's the end of the lecture today. So hopefully we've learned what isentropic efficiency is and how we can use it for either to find it, like we did with the turbine example, or to use isentropic efficiency to fix the real outlet state like we've done with the pump here. And throughout the rest of the course, you'll get experience doing both of these types of problems for different pumps, different compressors, and different turbines. So that's it for today. I will see you again next class. Thanks very much.